right, we are going to be working on chapter 6. So chapter 6 is about gases. And when we talk about gas, we want to see how gas molecules can create pressure. So every time you have gas molecules floating around, they're really far apart, but they're moving pretty quickly. Every time they hit a surface, they create a force on that surface, okay? So every time there's a force on this surface area here, we create pressure. So the more number of gases you have, the higher the pressure is going to be, okay? So, but it does say here the pressure gas depends on several factors, how many gases there are, what the volume is, and how fast they're moving. So we'll be talking about that throughout the chapter. So while we're talking about measuring gas pressure, the way we measure gas pressure is using a barometer. Here's a mercury barometer where if you had just the atmospheric pressure around here, the atmospheric pressure would be able to push on the mercury right here, and the pressure in the atmosphere that's pushing on it is going to push this mercury up the tube 760 millimeters in height. Okay, so this is where they start to say, the 1 atm or atmospheric pressure, which where we are right now, is 1 atm, and that equals to 760 millimeters mercury. Now, 760 millimeters mercury also equals to 76 centimeters mercury, because the difference between millimeters and centimeters is 10 times, okay? So I'm going to go ahead and write down over here, it's also 76 centimeters mercury. All right, so that's the barometer right here. So let's go look at the units here. Now on this common pressure units here, all you have to make sure you memorize is 1 atm, okay, equals to 760 millimeters mercury equals to 760 torr. Now remember, 760 millimeters mercury is also 76 centimeters mercury. Okay, so those are the only things you need to remember. So while we're at that, make sure you memorize this. So on this page here, all you gotta do is 1 atm equals 760 millimeters mercury equals 760 torr, and this one here equals to 76 centimeters mercury. Let's keep going. We want to talk about manometers. So manometers are basically an instrument here where we have gas in a flask, and it's going to be hooked up to a U-tube here, a little tube that's curved, and we put some mercury in here, okay? Now, if you take a look at this picture here, you can see if there's gas here and there's atmospheric pressure here, there's two opposing forces. It's kind of like instead of a tug of war, it's a push of war. This guy's pushing this way, this guy's pushing from out into here. So they're pushing on opposite side. Now, based on this picture here, if the liquid is more to the outside towards the atmosphere, that means what's in the flask is pushing harder. That means it's stronger pressure in the flask than the atmosphere. How much stronger? The difference in the height right here. Okay, that's how much stronger it'll be. So we use the manometer to measure pressure of the gas in the flask, basically how it compares to the atmospheric pressure. Assuming the atmospheric pressure is where you are right now, which would be around 760 millimeters mercury. Okay, so what we're going to do is take a look at a few examples here. Now, obviously, the answers are there, so I'm going to try to cover it right there. Okay, so let's take a look at the first picture. Let's zoom in a little bit. Is that better? All right, let's take a look at the first one. Flask pushing, atmosphere pushing. Seems like flask is pushing harder, right? So because the liquid is more towards the outside being pushed outwards, this guy can't push hard enough to push it back the other way. So that means the flask is higher pressure than atmospheric pressure. And we assume atmospheric pressure is at 760 millimeters mercury, okay? So remember, 760 millimeters mercury is what's outside. The inside is stronger than 760. So how much stronger? We measure the height difference here, and they say the height difference here is 70 millimeters. 7 centimeters equals to 70 millimeters. So that means the inside of the flask is 70 millimeters mercury higher than 760 millimeters mercury. So your answer over here, you would say the pressure of gas is higher than the atmosphere, which equals to 760 plus 70 millimeters mercury. Okay? Now let's take a look at the second one. In the second one here, you're looking at the gas is pushing and then the atmosphere is pushing. But in this case, the liquid's more towards the inside. So the atmosphere is pushing harder. That means the gas in the flask here is weaker than atmosphere. How much weaker? Measure the height here. 4 centimeters equals to 40 millimeters. Therefore, inside the flask is going to be 760 millimeters mercury minus 40 millimeters mercury. So you take a look at here, that would be our answer right there. Okay, so take a look at these two. And you can see that in this case here, this one atmosphere is pushing harder also. So the flask would be subtract how much? It would be 760 minus 20 millimeters mercury. And on the last example here, the flask is pushing harder. How much harder? 65 millimeters in difference. So that would be 760 plus 65 millimeters mercury. Okay, so you basically just have to see who's pushing harder, and the one that's harder will have the higher pressure. And we know the atmospheric pressure is 760. So that's the answers right there. So let's talk about some simple gas laws. Okay, we have 3 of them. Then we want to combine the simple gas laws to make the ideal gas law. So let's talk about all 3 of them first, and then we'll do the math. Well, we'll do the math as we go, and then we can also talk about the ideal gas law problems. So the simple gas laws are really simple. So it's just basically 2 parameters are changing each time. Okay, so the first one is called Boyle's law. Boyle's law tells you that when you observe the pressure change of a gas, it's always the opposite or inversely proportional to the volume. Okay, when you increase the volume, the pressure drops. When you increase the pressure, the volume, if you increase the pressure, the volume drops. So it's basically the opposite. Okay, so if P goes up, V goes down by the exact same factor. If P goes down, V goes up. So it's always the opposite. So because of that relationship, P times V is a constant right here. Now, this is here, P times V is constant. You gotta make sure everything else is, only thing changing is P and V. So pressure and volume are the only things changing. Your temperature must not change. Your number of moles of gas must not change in the sample. Okay, that's the assumption. When you change pressure and volume, temperature and number of moles are not changing for this case. Only 2 things that are changing. Now, because P and V are opposites, you use the formula P1 times V1 equals to P2 times V2, where this is the original pressure, original volume, the new pressure, and the new volume. Okay, so let's take a look at how we can explain why the volume and pressure are opposites. If you take a look at this picture here, originally we have this picture, everyone's happy, and then you decide, okay, well, I'm gonna put a heavier weight on it. We're gonna squish it down. The pressure now increased. Why did it increase? The number of moles didn't change, right? But now the pressure increased here. Why did the pressure increase? Now, do you see that the volume has now gotten smaller? The volume they get smaller. So when you increase the pressure, the volume gets smaller. And we also say you can see because the space is smaller now, the gas hits the walls a lot more often than it would be over here. So this one here has a higher pressure. Okay, so volume and pressure are always going to be the opposite effects, opposite trend anyway. So what's important and cool about Boyle's law is comes to an application when you're diving. So when you're diving below the surface, the lower you go, the deeper you go, the pressure changes. It increases. It says here at 20 meters, the total pressure is 3 atm. That's crazy, right? So it increases a lot every time you go deeper and deeper. So when you, that's why when you dive, you need to use your tanks and has a regulator so it can deliver the air in the same pressure as your surrounding. Now, if you are trying to basically rise up to the surface, they always tell you exhale when you're rising, because if you held your breath and you rise, you just went up really quickly, that air in your lungs is going to expand because pressure was high here, volume is small. When you go up there, pressure is lower, the volume is going to be bigger and it's going to expand your lungs, and that's not a good thing. You can cause damage that way. Okay, so that's one application of Boyle's law. So we can go ahead and move on. We'll do a problem with Boyle's law. We'll do all the simple gas laws all together after we talk about all of them. So Boyle's law is P times V and equals to P times V, basically. Okay, let's look at Charles' law. Charles' law talks about volume and temperature. Now they're saying volume and temperature are changing, but pressure and number of moles must stay constant in this case. Okay, now because every time they're saying when volume goes up, temperature goes up. It goes up hand in hand. So when you do the equation, you have to do V over T equals to V over T. And this one's the original volume and temperature. This one's the new one. Okay, so let's go to this next slide here. Oh yeah, what's important on this here, this temperature here? Always, always, always use just Kelvin. Only Kelvin, okay? You don't want to use any other unit on the bottom here. Make sure you use Kelvin. All right, so Charles' law here tells us something really cool here too on your experiment. If you were to record your volume and temperature change for like, you know, a different, basically different lines here, you have volume of 1 gram of oxygen at a certain pressure, and then you did something else at a different pressure. So and another, so these three of them are 1500. So it doesn't matter what pressure it is, but as you seem to, when you plot the volume versus temperature, you have this line here, you have that line, all the lines are different, right? But if you follow through with the same slope, you extrapolate it all the way back, okay? When it hits 0, they all end up at the same temperature. And that temperature here is absolute 0, which is 0 Kelvin. And we call it 0 Kelvin is absolute 0. So over here, this is negative 273.15 Celsius. So let's take a look at the molecular picture of Charles' law. Basically, why is the volume and temperature changing hand in hand? When something is high temperature, there's a lot of kinetic energy. They're bouncing all around. They can make the balloon bigger. So basically, temperature is high, lots of energy, volume is bigger. Temperature is low, lower kinetic energy, not as much energy to bounce around the walls. The balloon volume is smaller. Okay, so this experiment here, you obviously can use a balloon, but a lot of people just take a can, just a soda can, and then you fill it up with some gas that was hot, and you throw that can with the hot gas into some ice water, and the can will literally shrink. Okay, so that's Charles' law right there. Now remember, Charles' law is V1 over T1 equals to V2 over T2. One important thing is your temperature must be in units of Kelvin. All right, let's take a look at the third simple law that we have. It's called Avogadro's law. Avogadro's law tells you that volume and number of moles of gas will be changing at the same rate proportionally, okay? So because they're changing at the same time, the more moles you have, the bigger the volume will be. If you have constant pressure and temperature. Only two things are changing, all the other parameters must stay constant. So if volume and number of moles are changing, pressure and temperature must stay constant, okay? So more gas molecules will give you a bigger volume here. So that's why it's V1 over N1 equals to V2 over N2, okay? So that's that for our three laws here. So I want to go ahead and write them all out. We'll do problems for each simple gas law, and then we'll combine them to make the ideal gas law, okay? So first one we wanted to do, let me zoom out a little bit. We want to talk about Boyle's law. So Boyle's law was what? P1 V1 equals to P2 V2 because what? Pressure and volume were opposites, okay? And it says a cylinder with a movable piston has a volume of 7.25 liter under 4.52 atm. What is the volume of the cylinder if we decrease pressure to 1.21 atm? Okay, so in this thing here, we have pressure and volume. So important thing here is when you're using anything with the gas laws, we do end up using the ideal gas law. And I want you guys to go ahead and remember every time you have pressure, let's go ahead and stick with this unit that we use, that's standard. We will use ATM and volume will be in liter. Okay, the units you want to go ahead and use here, this one will be in ATM, this one will be in liter. Okay, just keep that in mind. So let's go ahead and put it in P1 V1 equals to P2 V2. So this is P1, that's V1, that's P2, and we'll look for V2. So P1 is 4.52 ATM times 7.25 liter equals to 1.21 ATM times something we don't know, liter, okay? So solve this by taking 4.52 times 7.25 divided by 12, divided by 1.21, you get 27.1 liters. That's how you would do it. So keep in mind Boyle's law, ATM and liter, P1 V1 equals to P2 V2. Now we want to go to Charles' law. Charles' law is a sample of gas has a volume of 2.80 liter at an unknown temperature. When the sample is submerged, what is it submerged? In ice water at temperature equals to 0.00 Celsius, its volume decreased to 2.57 liter. What was the initial temperature. We want it in Kelvin and in Celsius. So when you do Charles' law, always make sure you use V1 over T1 equals to V2 over T2. And this one here you use liters, this one here you use Kelvin. Okay, so that's Charles' law right here. So now we have V1 is 2.8, and then we don't know T1, we're looking for that. T2 is over here. That's 0 Celsius, but we have to change it to Kelvin. And then V2 is 2.57 liter. Okay, so what's 0 Kelvin? 0 Kelvin is going to be 273. 0 Celsius is 273 Kelvin. Okay, so I'm going to go ahead and write it out. So 2.80 liters, and we don't know what the initial temperature is, not V, T. And then we have 2.57 liters over 273 Kelvin. Okay, so then you solve for T1. How do you do T1? T1, you'll basically have to take 2.80 times 273 and then divide by 2.57, okay? So when you do that on your calculator, you get 298 Kelvin, and that equals to 25 degrees Celsius. So hopefully everyone's pretty good with your algebra. You know how to do that. So that was Charles' law. Now let's go ahead and solve for Avogadro's law. And it says V1 over N1 equals to V2 over N2. This will be units of liters. This will be units of moles. Okay? And then we want to go ahead and write a question out. A 4.65 liter helium gas contains 0.225 moles of helium. How many additional moles of helium gas must we add to the sample to obtain 6.48 liter in volume, okay? And then it says assume constant pressure and temperature. So the question is saying, originally I have this volume and this many moles. How many more extra moles of helium gas do I need to add to 0.225 moles so I can get 6.48 liter, assuming the pressure and the temperature are constant? So you use this formula here. We gotta find a new number of moles, okay? But they didn't say what's the new number of moles. They say how many moles must you add to the original. So once you find N2, you must take N2 and you gotta take that out, take out 0.225, okay? That's how you can get the moles of helium that you have to add. So let's go ahead and just do that first. So V1 is 4.65 liter over N1 is 0.225 liter, okay? And then V2 is 6.48 liter over N2. So we have to solve for N2 here. N2, when you work on a calculator, it'll be basically you get 0.314 moles. So to do that, you have to take 6.48 times 0.225, and then you gotta divide by 4.65, okay? And then you can get the answer that way. So hopefully everyone's aware of how to do this. And once you get this new moles here, that's not the answer yet because they're saying how many moles do you need to add to get to this number. So if we already have 0.225, how many moles do we need to add to get to this? So all you gotta do is take 0.314 moles. You gotta minus out what you already have to be able to find how much you gotta add to it. So what you gotta add is 0.089 moles of helium gas. And that would be the answer for that question, okay? So let's take a look at all these three simple gas laws and we wanna combine them into the ideal gas law, okay? So I wanna show you how it's related all to the ideal gas law. So ideal gas law, PV equals to nRT. This one is pressure in ATM, volume in liter, N in number of moles, R is a gas constant. Okay, what's the gas constant here? You will find this on your periodic table. There's going to be two R's on there. You will use this one. R equals to 0.08206 liter times ATM over moles times Kelvin. Okay, so why? See, this is why we have to use liter ATM, moles, and then Kelvin for the temperature. Because we're trying to match the unit of R from the periodic table. Okay, so that's why we gotta, if you forget what unit you're supposed to use, just look at the R and see what the 4 units are, and those are the units you have to use. Now, if they say you wanna do Boyle's law, P or V are changing, and then number of moles and temperature are not changing, and of course that's not changing because that's a constant. So Boyle's law says P1 V1 equals to P2 V2, right? So basically, these two that are changing are on one side, nRT are constant. Those are not changing. So whenever you have the scenario of another PV, so pressure 1, pressure 2, volume 1, volume 2, they will always end up coming back to the same value here. So basically it's based off of this equation here. You just put the things that are changing on one side, the things that are not changing on the other side. So that's how you can get P1 V1 equals to P2 V2. Okay, that's the first one. And then the second one, we had PV equals to nRT. So this is Boyle's. And then we want to do Charles. Charles is V and T, right? So we said to get V and T on one side, you have to do V over T equals to NR over P. And V1 T1 equals NRP. This is constant right here. So you can always just say, well, the second set of my temperature and volume is going to come back to this value as well. So we say V1 over T1 equals to V2 over T2. Okay, that's how we get Charles' law. And then Avogadro's law is PV equals nRT. We're talking about volume and number of moles. So you say V over N equals to RT over P. Okay? And then this is constant right here. So V1 over N1 equals to V2 over N2. That's how you get these three laws. Okay? Now, these are the three laws. Now, what if you had a question where you have more than two things changing? Say, for example, if you have three things changing, where you have pressure changing, temperature changing, and you have volume changing. Okay, let's say you have these three things. So no matter what combination of things that are changing, you can do this. You can even do
basically all four things are changing and then keep R on one side. You can solve it that way too, but just basically if you had three, you could do it the same way. So we just have to rearrange it. So if you have P, V, and T on one side, and you need, these are all changing. These are the changing stuff. So PV equals to nRT. My formula would be PV over T. P1 V1 over T1 equals to NR, okay, equals to P2 V2 over T2. And this here is constant. So the formula I would use will be P1 V1 over T1 equals to P2 V2 over T2. Now the combinations are endless. You could do PV and N, and then VT and N, whatever combinations you want. You can still write an equation from it. As long as you do the changing stuff on one side, the constant stuff on the other, and then we do the equations with the changing stuff. Okay, so let's go ahead and work on a problem here. I'll write the question out. It says a balloon filled with helium gas at 20 degrees Celsius occupies 2.91 liters at 1.00 atm. Okay, and then it says this balloon, the balloon, is immersed in liquid nitrogen. So have you guys heard of liquid nitrogen? Super cold stuff. Okay, you can make Dippin' Dots using liquid nitrogen. If you drop your ice cream into liquid nitrogen, it completely solidifies as it drops in. Like drops of ice cream freezes in little spheres. Kind of cool, but kids love it. Does it taste different? I don't know. You guys tell me. Anyway, so the balloon is immersed in liquid nitrogen, really, really cold. At what temperature? At negative 196 Celsius. That is so cold. While raising pressure to 5.20 atm. That's really high pressure because 1 atm is where we are, 5.20, that's a lot higher pressure. It says, what is the volume of the balloon in the liquid nitrogen So we have to calculate the volume. So originally it was almost 3 liters. It was 2.91 liter. So just imagine that, I guess that's 3/4 of a gallon, kind of almost. So it's not like almost as big as a milk jug. This is a regular size balloon, right? So let's see what happens when you lower the temperature that much and increase the pressure by that much. Will the balloon shrink? Does it sound like it's gonna shrink? Let's take a look, okay? So my guess is it's gonna shrink because the colder it is, the volume will get smaller. Increase the pressure even more, the volume will get even smaller then. Because based on the laws that I knew about Charles and Boyle's law, okay? Anyway, let's go ahead and figure out what we're gonna do here. So 3 things are changing. You got temperature, you got volume, and you got pressure, okay? And then the new temperature is here, the new pressure is here. We got to find a new volume. Now, what's the trick here? They use Celsius. You cannot use Celsius in your calculation, okay? You must use what unit? You must use Kelvin, okay? So this here has to be Kelvin, this one has to be in liter, this one has to be in ATM. The other units are correct, just the Celsius is wrong right there. So a lot of times people forget and just plug in that number right there. Then you find out that, you know, you create some problems because your units are wrong. So let's go ahead and use this equation here because we are changing P, T, and V. Okay, so my formula I'm going to use is P1 V1 over T1 equals to P2 V2 over T2. So I feel like this way is faster. to do it. Now you could do it another way. You use PV gas and nRT, you solve for the number of moles, and then you take the number of moles and plug it into the next PV gas nRT and solve for the new volume. You can do that. That just takes way longer in my opinion. Okay, so I like to show you guys a shortcut. Basically, make your own equation and save a lot of time. Okay, so let's go ahead and plug all these values in. So 1 ATM is the original pressure. My original volume is 2.91 liters. And then the temperature is 20 degrees Celsius. So that's going to be 293 Kelvin. And then 5.20 ATM is my new pressure. I don't know my new volume. I'm looking for that. And my temperature of negative 196 Celsius. Negative 196 Celsius. And you got to add 273. And that will give you 77 Kelvin. Okay, I guess I should write down 20 Celsius plus 273 is 293 Kelvin. That's how I got that, okay? Anyway, let's put that down here, 77 Kelvin. Okay, so this kind of math here, again, is like solving like what we were doing earlier. Now you have to solve for V2. So to get V2, I'll write it out for you guys. So you have to do 1.00 ATM times 2.91 liters divided by 293 Kelvin. That stuff stays the same. And then you have to solve for V2. So you have to then multiply with 77 Kelvin on the top. And then you also have to divide by 5.20 ATM on the bottom. So if you don't know how to do this, you need to brush up on your algebra. Try to get help. There is a lot of math help on dynamic study modules as well online for extra credit. So it's a really good practice. You learn, you brush on your math, and you earn extra credit at the same time. That's really, really helpful. And of course, there's tutors. You can ask me. I'll try to teach you math. Although I'm not a math teacher, I learned this before. I should be able to help you with it. So feel free to ask questions. Ask questions anytime you need to. We're here to help you. Anyway, so we put all this in here, plug it in your calculator, and you're going to solve for volume 2 as 0.147 liters. And that is super, super tiny compared to 2.91 liters. So our guess was correct when we said it was going to shrink. Okay, so hopefully everyone's good so far. Now we want to go ahead and talk about something called the standard temperature and pressure, so standard conditions. Okay, so I'm going to show you the slide we're on now. Anyway, ideal gas law slide was on slide number 21. So I wrote all that out down in the book anyway, so you have that already. So let's talk about standard conditions, okay? We're on slide number 22 now. Because we use standard conditions so often, we just go ahead and label it. So these are the standard conditions when we talk about our gas chapter here. Our standard pressure will be 1 ATM because a lot of times our experiments are at 1 ATM unless we go into some pressure change when we change the pressures, okay? And then standard temperature is 273 Kelvin or 0 Celsius. So one thing I do want to tell you guys is, you know, where we are at sea level is 1 ATM. As you go up higher and higher elevation, the atmospheric pressure does drop. It drops like, you know, depending on how high you are. The higher you go, the less, I guess the air is thinner, you know how they say it? That's because there's actually less gas molecules, so your pressure, atmospheric pressure drops. But our standard conditions are 1 ATM, 273 Kelvin, okay? So with that being said, every time you have standard temperature and pressure, we have one cool thing that we've observed. I guess I'll show you the picture after this. At STP, we define STP as 1 ATM, 273 Kelvin for the gas chapter, okay? Any gas, I don't care what kind, as long as it's ideal, any ideal gas at STP, that's what we're talking about, ideal gas law. 1 mole of that gas equals to 22.4 liter. This guy here, 22.4 liter, is called the molar volume of gas at STP. Okay, so we have that going for us. Now that we know all of this stuff, we can start doing calculations that has problems with gas at STP. Okay, so I want to show you an example of that. Actually, I'll show you 2 examples. So let's start with the first one. Determine the maximum amount of K2CO3 that can be produced the percent yield of K2CO3 if 21.8 grams K2CO3 is produced from reacting 27.9 grams of KO2 with 29.0 liters of CO2 at STP. Okay, I'll go ahead and give you the equation for KO2 plus 2 CO2 equals to 2 K2CO3 plus 3 O2. And then we'll go ahead and give you the molar masses for each one of these guys. I guess I'll write on the side. KO2 is 71.10 grams per mole. K2CO3 is 138.21 grams per mole. CO2 is 44.01 grams per mole. So we have that, all that information here. Okay, so this is a stoichiometry problem, but now they're throwing in gases at you. So stoichiometry not over yet. Gas chapter still has it. So let's take a look at how we can solve this. It says here, number 1, determine the maximum amount of K2CO3 that can be produced. That's the theoretical yield, right? So number 1, we have to look for the theoretical yield if we have this reactant and that reactant. So let's go ahead and do that one first. And after we get the theoretical yield, they want you to find the percent yield because they gave you the actual yield. Okay, so now my goal is to first get the theoretical yield. So I have to go from both my reactants. I'm going to start with my first one. So my first one, I have 27.9 grams of KO2. And then I have to turn it to moles of KO2. Write down the map here. And then moles of KO2 to K2CO3. And then I can get grams of K2CO3. That one's, we can do that. And then if you have that one right there, 29.0 liters of carbon dioxide. You want to use the fact that 1 mole of gas is 22.4 liters at STP, right there. Okay? You want to turn it to moles of CO2 that way. And then you do the mole to mole ratio to get moles of K2CO3. And then we can turn it to grams of K2CO3. That way we can find the theoretical yield. When which one is going to be the theoretical yield? The smaller number, because after you make the smaller amount, you run out of stuff to make more. So we have to go ahead and work these two out. Okay, so let's go ahead and start. 27.9 grams of KO2. Oops. All right, we have that. Only want to use the molar mass. 71.1. 1 mole. Mole to mole ratio is 4 to 2. You guys see that? Okay. And that one, 138.21 grams. It's still 1 mole. So you can get the grams of K2CO3 there. You should get 27.1 grams. We're not done yet. We gotta do the next one, okay? Because we have to compare. The smaller one will be the theoretical yield. 29.0 liters CO2. One mole is 22.4 liter because it's at STP. And then we'll do the mole to mole ratio 2 to 2. And then we'll convert it to grams again. Punch this in your calculator. You will get 180.0. Actually, just 180 point like this. Well, it's not 180.0. I lied. We're gonna change it. I got and keep 3 sig figs, 179. Anyway, that number didn't matter because that's way too big. That's impossible. Once you make 27.1 grams, you run out of KO2. This is my limiting reactant. That's my theoretical yield. Okay, so we got that part. That's the first one. And then the next one, they asked you to go ahead and calculate, what did they want you to calculate? They want you to calculate percent yield, right? They said how many grams was actually made. They made 21.8 grams. So percent yield equals to actual over theoretical yield times 100. So what do we have? 21.8 grams over 27.1 grams times 100. And we are going to get 80.4%. That's my percent yield. And that would be the question that we had to solve for. Now, what if they were really sneaky and they say, well, who's the excess reactant and how much is left over? Well, that right there, right? This is the excess, and how do you find what's left over? You find out how much of this guy was used, assuming all of this is used up. So you have to pair KO2 with CO2, find out how much CO2 was used if all 27.9 grams of KO2 was used. And then you take 29.0 liters minus whatever liters of carbon dioxide that was used up. Okay, that's how you would find how much excess was left over. So that's one question here that has to do with STP. I would like to show you guys another question that you can have if you had an STP question, okay? So here's one more. It's a combination of ideal gas law and STP. It's kind of cool, and plus the documentary that we just learned, and you really need to practice. So here's another one for practice. Determine the volume of SO2 at STP formed by the reaction of 96.7 grams FeS2 and 55.0 liter of O2 at 398 Kelvin and 1.20 ATM. Well, one of it is STP. This one here is not a STP. Okay? And they say molar mass of FeS2 is 119.99 grams per mole. That's a lot of nines. And it says assume 100% yield. Well, that's nice because if it wasn't 100% yield, my question just got even more complicated. So that's a good thing. But you do need the equation. So I'll write the equation out. It's 4FeS2 plus 11O2 goes to 2Fe2O3 plus 8SO2. That's it. Okay. And all these here, these are gas. That one's a solid. This one's a gas. Okay, so we have this question here. They want to find the volume, so how much product, okay, at STP. So you just basically gotta find the moles of SO2 and then convert it to volume, where 1 mole is 22.4 liters. So what are you reacting though? We got 96.7 grams of this guy. And we got a bunch of parameters for oxygen. It was 55 liters, 398 Kelvin, 1.20 ATM. Now all these values here, you use PV equals nRT to give you the number of moles. So this one here, you can turn into number of moles easily using the molar mass. Once we do that, we can figure out the theoretical yield, which is the smaller amount, right? Theoretical yield SO2. And then from there, from theoretical yield, we'll make sure we convert that the theoretical yield to volume, because each one is 1 mole is 22.4 liter. Okay, so let's go ahead and try the first one. So this one here, we gotta see 96.7 grams of FeS2. How many liters of SO2 can you make? So you have to go ahead and change that to moles. Use the molar mass. The molar mass is given, so 1 mole FeS2 is 119.99 grams FeS2. Then once you know the moles-mole ratio is 4 FeS2 to 8 SO2. 8 SO2, oh, forgot my moles. And then 1 mole of SO2 is going to be 22.4 liters because it's at STP. Okay, let's find out what the volume is here. This one is 36.1 liter of SO2 possible. That's the first option. What's the second option? We gotta find out how many moles of oxygen first. Because once you get moles, you can do the mole-to-mole ratio. So let's do that. So for oxygen, we have to do PV equals to nRT. So oxygen pressure is 1.20 atm. Volume is 55.0 liter. Equals to N, we're looking for that R is 0.08206 liter atm moles Kelvin. And temperature was given as 398 Kelvin. We solve for N here, okay? So N here, basically if you do your calculator, you have to say 1.20 times 55 divided by 0.08206 divided by 398. And you should get 2.02 moles of oxygen, okay? Once you get that moles of oxygen, we can go ahead and take the mole to mole ratio. I'll show you that right here. It's 11 moles of oxygen to make 8 moles of SO2. So we'll do that. 2.02 moles of O2. 11 moles of O2 is to 8 moles of SO2. And then 1 mole of SO2 is going to take up 22.4 liters SO2. You can get the volume right there. So let's see. This one here ends up being 32.9 liter SO2. You're like, huh, it's a good thing I didn't pick the first one because that one was too high. This is my theoretical yield. And the question was asking for theoretical yield because it says determine the volume of SO2 at STP formed by this reaction. Assume 100% yield right there. If they said it wasn't 100% yield, then whatever percentage, you just have to take percent. This is theoretical yield and you just take percentage of that, okay? That is how you do some problems with STP in stoichiometry. Now, the next thing we want to talk about is we want to talk about density of gases. I want to show you the picture of it first, okay? This is a molar volume picture. You see how helium, xenon, and methane didn't matter. They're all the same volume because they're at STP. So it doesn't matter what kind of gas it is, okay? If it's a STP, it's ideal gas. The volume for 1 mole is 22.4 liters. Okay, so here's another cool observation. So because at STP, 1 mole ideal gas takes up 22.4 liters. Okay, that's this part here. I want you to find density of nitrogen gas, just an example, at STP. You're like, really? How? Okay, so let's think about what the meaning of density is first. Density is mass over volume. So we have to somehow get grams of the gas over a liter of the gas. Grams of N2 over liter of N2. Now density is an intensive property. Agree? Intensive property does not change with the amount. A little bit of gas, the density is blah, blah, blah. A lot of gas, the density is the same, blah, blah, blah. Okay? So basically, what is a convenient amount to use then? If it didn't matter how much gas you had, I would pick 1 mole of gas, okay? To find the density of 1 mole of gas is to find the density of all amounts of gas for that nitrogen. So if I wanted to look for 1 mole of nitrogen, what's the volume of 1 mole of nitrogen? 1 mole of N2 at STP takes up 22.4 liter. Now, 1 mole of nitrogen at STP, how much does it weigh? It weighs whatever the periodic table says, okay? Each one of them is 14.01, so 2 of them is going to be 28.02. Ta-da! Grams per liter, right there, okay? So the density is 28.02 grams over 22.4 liter, which will give us 1.25 grams per liter for the density. So therefore, based on this here, density of gas, ideal gas, at STP equals to molar mass over molar volume. That's a short story, but a lot of times you forget why, you know? So if you sat down and reasoned it through, it's probably going to be easier to remember. So I want you guys to make sure you practice doing this, okay? Now, so that's an STP, super easy to get the density. What if I asked you to get density at something that's not STP? You're like, oh my gosh, why? Well, because we have to learn it, okay? And then you can go home and tell everybody, well, you know what? I can calculate the density of this gas if you let me know what the parameters are. Okay, so we are going to calculate another gas density, but now this time is not going to be at STP, okay? So I want to show you how we can get that formula. There's a formula, we'll just memorize it, but I wanted to show you how we get it because it's kind of cool. It's based on ideal gas law. So you have PV equals to nRT. Okay, and then, so let's rearrange it a little bit. To get it closer to density, I'm going to put the moles over the volume. Okay, and then that N over V on one side, and then I'll have RT P over RT on the other side. Okay, so we have this here. This is moles. This is liter. I'm really close to density. How can I get moles to turn to grams? How can I do that? To turn moles to gram, you literally multiply with molar mass. Agree? So why don't we go ahead and multiply this with molar mass on both sides? N moles times molar mass will give you grams, and then liter, and that gives you P over RT times molar mass. And this here is density. So density equals to P over RT times molar mass of the gas. Okay, so we are going to do that problem. So let's go ahead and now give you a set of parameters. We're still going to look for nitrogen, okay? We'll do nitrogen gas, find its density at 125 Celsius and 755 millimeters mercury. So definitely not STP, okay? So we have to put all the information in now. When you do this units here, we have R, and the units for R is liter, ATM, moles, and Kelvin. This has to be changed to Kelvin. This has to be changed to ATM. Always change your units. If you use the wrong units, you're not going to be able to get the right answer. Okay? So we can go ahead and convert these guys here. Let's go ahead and do that. 755 millimeters mercury. You want to change it to ATM. One ATM is 760 millimeters. And you get 0.993 ATM. And then we want to go ahead and turn 125 plus 273. You can get the Kelvin is 398 Kelvin. Okay, so then we can go ahead and plug it in. Density of nitrogen now equals to P 0.993 ATM over R is 0.08206 liter ATM moles Kelvin. Temperature is 398 Kelvin. And the molar mass is 28.02 grams per mole. We did that earlier for the previous one, right? So, and then you see how all the units cancel out. Moles and liter cancel out. Moles, well, liter stays there. Moles and moles. And then grams and liter stays. ATM cancels off. K and K cancels off. Okay? So you do have your answer for density. It's going to be in units of grams per liter. And you get 0.852 grams per liter of nitrogen. So it changes. So earlier it was 1.25 at STP. When it's not STP, it just changes depending on what your parameters are. Okay? So that's how you do density of gases. Now, let's go ahead and talk about how we can find molar mass of gases. Why would we want to find molar mass of gas? Because sometimes if you don't know the identity of the gas, if you find a molar mass, you get one step closer to finding the identity, because you can kind of, you know, if you have a few choices of gases, you can just find the molar mass, and then whichever one matches that same molar mass, you'll know that's your identity. Okay? So molar mass of gas is useful to identify unknown gas. What's the unit of molar mass? Grams per moles. So we have to find a way to put grams on the top, moles on the bottom. That's how you would get the molar mass. Okay? For density, it was grams per liter. So I'm going to give you a question on molar mass. We'll try to work on it together. A sample of gas has a mass of 0.311 grams. Its volume is 0.225 liter at 55 Celsius and 886 millimeters mercury. It's 55.0 Celsius. And then find molar mass. Find molar mass of this gas. So we have to find molar mass, where molar mass is grams per moles. We already have the grams part. Okay. We just gotta look for the moles. Okay, so let's look for the moles. PV equals nRT will be used. But all units are, these units all need to be changed. This one needs to be changed to Kelvin. This one needs to be changed to ATM. That one's fine. Okay, so let's go ahead and change the units first then. So 55 degrees Celsius plus 273, that will give me 328 Kelvin. And then my pressure that I have to change, 886 millimeters mercury. And then 1 ATM is 760 millimeters mercury. That is going to equal 1.17 ATM. Okay, now that we have the ATM and Kelvin converter, we can go ahead and plug it in here. Okay, P is 1.17 ATM. V was given as 0.225 liter equals N. We're trying to find N there. And R, 0.08206 liter ATM moles in Kelvin. This one here, you look from the periodic table, and then eventually you do it enough, you'll remember the number. And then temperature was 328 Kelvin. Ooh, got real close there, almost ran out of space. Anyway, to get number of moles here, you literally will take 1.17 times 0.225 divided by 0.08206 and also divided by 328 Kelvin. And you will get your answer as 9.78 times 10 to the minus 3 moles. Once you get that, we will stick that over here. So our molar mass will be 0.311 grams divided by 9.78 times 10 to the minus 3 moles, which will give us a molar mass of 31.8 grams. That will be our answer right there. And then if you get, to a point there, they ask you what's the identity of this gas, maybe they'll give you A, B, C, D choices. Make sure whichever gas you pick has the same molar mass whenever you look it up from the periodic table. Okay, so that's how we would do molar masses for gases. Now, let's go to the next part of this chapter. We're getting to the last parts now, so we're almost there, almost there. So it has to do with partial pressures of gas. They're saying that gases here they don't really care about the identity at that point. It says here, when gases are mixed together, the molecules behave independent. So all the gases will take the entire volume of the container, okay? And then if they're all at the same temperature, they'll have the same kinetic energy. So remember, anything that has the same temperature will have the same average kinetic energy, because kinetic energy is the hotter it is, the faster it will move, more energy, right? So that's why it's the same over here. So therefore, in maybe like in a container that has the same temperature, okay? So we can start adding these gases as if they add up. So partial pressures, they can add up the moles of it. When the moles add up, the pressures will increase as well, okay? So basically, they're saying that if you can add the pressures together, you can also add the moles together, and they're related. They're changing at the same rate, okay? So let's go ahead and take a look at some equations here, and then we'll just do examples. It'll make more sense. So basically, if I have, like in my flask, I have 3 gases, A, B, and C. And then A gas will be certain ATM, maybe 1 ATM. B is 2 ATM, and C is 3 ATM. What's the total pressure in here in the container? You would just add 1, 2, and 3 up, whatever the pressures are. Okay, so they're saying that you can add them up individually according to the gases. They just all behave the same way. They have the same kinetic energy. They just can be added up together. They behave independently. Okay, so basically, the more moles of gas you have, the higher the pressure will be. So pressure of A will be dependent on the moles of A, and then the volume is fixed because they're in the same flask. R is constant, temperature is constant because you're not changing the temperature for each one. So they're all constant. So you can see how the pressure and the number of moles are directly related. Okay, so if we say you can add the total pressures up, that also is related to the addition of the total of the gases, moles of gases. Okay, so then we can say, well, P total is equal to, you can count pressure A plus pressure B, or you can just take total moles of A and B and then just times RT over V. You can get the same answer. So the point of this is they're saying when you have multiple gases in a container, the gases can be added up on a mole ratio or on a pressure ratio. They're going to behave the same way. They're going to add, they're going to be changing at the same rate. Okay, so because they're all interconnected like that, we can start saying that pressure of one gas, the ratio of pressure of one gas versus the total pressure is going to be the same as the ratio of moles of that one gas over the total moles of all the gases. Okay, now when you do this ratio here, this ratio is called mole fraction. So mole fraction is this sign here. Mole fraction of A is moles of A over total moles. And then that can actually give you the pressure of A, because that's related. It's like, so PA over P total is mole fraction. So mole fraction times P total is PA right here. Okay, so that's another equation right here. So we'll be using mole fractions, and then we'll use total moles. We can add up the pressures, add up the moles, or we can use mole fractions to do it, depending on the question. So we'll do a few questions here, and we'll get used to it. And you will have to practice, okay? All right, so the first one we want to do is has to do with a tank mixture of gases, 3 different gases, okay? So 1 liter of a mixture of helium, neon, and argon. So helium, neon, and argon, 1 liter mixture. All these gases. There's no period there. Has a total pressure of 662 milliliters mercury at 298 Kelvin. If the partial pressure of helium is 341 millimeters mercury and partial pressure of neon is 112 millimeters mercury, what mass in grams of argon is present in this mixture? So there's 3 gases, okay? And the total of 3 gases pressure is 662. They gave you the first 2 pressures for the other 2 gases. You can get the gas pressure of argon, agree? So P total is the pressure of P of helium plus P of neon plus P of argon. So we know these values here. So it's 662 equals, the helium is 341. Neon is 112. So P of argon is what's left over. Let's calculate that. That would be 662 minus 341 minus 112. You get 209 millimeters mercury. Okay, so now that we get the pressure of argon, we can get grams of argon from that, because we can find the moles of argon. We can use PV equals nRT, and then we can use molar mass to convert it to grams. Okay, so if I want to use PV equals nRT, I got to make sure this is in units of ATM. That's good. Now remember, why am I using volume as 1? Because all these 3 guys here, their volume is 1. So volume of argon is 1 liter. Argon is going to be at 298 Kelvin. And then the pressure is whatever it is in liters, in ATM. So we're going to change it. So 1 ATM is 760 millimeters mercury. Let's go ahead and change that. That will be 0.275 ATM. Okay, so now that we have that, we want to do PV equals to nRT of just argon. So I guess I'll put P of argon, V of argon, N of argon, R, and T of argon. Okay, and the pressure of argon was 0.275 ATM. The volume of argon was 1 liter. because all the gases took the same volume. Number of moles of argon is what we're looking for. R is 0.08206 liter ATM moles Kelvin. And then the temperature was 298 Kelvin. Okay, so to get n of number of moles of argon, all you do is to take 0.275 times 1 divided by 0.08206 and divided by 298. Okay, and you can get number of moles here as 1.13 times 10 to the minus 2 moles of argon. And then once you get moles of argon, we can go ahead and change it to grams of argon, right? How do we change it? We use 1 mole of argon weighs 39.95 grams of argon. Now this here you can look from the periodic table. Okay, so argon is right here on the periodic table is 39.95. So then we can get the mass of argon, and the answer is 0.451 grams of argon. Okay, so basically the idea is you can add the pressures up. Okay, so let's do another one. This time we want to do one with the mole fraction in it, okay? And the mole fraction one, I'll write the question out. A mixture of xenon, krypton, and argon has a total pressure of 6.70 atm. What is the mole fraction of Kr if the partial pressures of xenon and argon are 1.60 atm and 2.80 atm respectively? Okay, so give the answer choices A, B, C, D, E. 0.174, 0.570, 0.481, 0.256, 0.343. Okay, so now that we have all of this, very serious today. Too much. Okay. All right. Anyway, so we got this here. So we want to get pressure of krypton. We got to get the pressure of krypton first. Okay, so pressure of krypton is total pressure minus P of xenon and P of argon, which is 6.70 atm minus 1.60 atm minus 2.80 atm. And this will give me 2.3. Remember, I said, well, the previous slides that we were talking about, it says, if you wanted to get the mole fraction, P of krypton over P of total is equal to N of krypton over N total, which this one is really just mole fraction of krypton. Okay, so we can get the answer. So mole fraction of krypton is 2.30 atm divided by 6.0 atm. And the units cancel off. Mole fraction has no numbers, just a fraction of 1, 0.3. That's how we use mole fraction. Okay, so let's try another one that has the mole fraction. things. And there's many ways to do this one, but I'll show you like, the way I would do it. I like to do it a little bit faster. There are other ways to do it too. Just longer math. I tend to find a shorter ways a little bit. So let's write this next question down together, okay? So it says a scuba diving tank of 12.5 liter contains a helium, oxygen, it's called Helios mixture. It is made up of 24.2 grams to 24.2 grams of helium and 4.32 grams of oxygen at 298 Kelvin. Calculate mole fraction and partial pressure of each component and the total pressure. The total pressure. Okay, so let's work on that. I guess I should write down the formulas over here so you can remember. So remember we were talking P of the gas over P of the total equals to N of the gas over N of the total, which is the mole fraction of the gas. Okay? And then if you take that, and that together, P of the gas equals to mole fraction of the gas times P. Okay, so we have 24.2 grams of helium, okay? And we have 4.32 grams of oxygen. Let's go ahead and convert them to moles first. Because you need mole fraction, right? Gotta do that. So let's go ahead and do that. Helium, the molar mass is 1 mole of helium is 4 grams. From the periodic table, 1 mole of oxygen. A lot of people forget they put 16. There's 2 oxygens there, so it's 32. Okay, don't forget that. That's a pretty common mistake, surprisingly. But this one is 6.05 moles of helium, and then you get 0.135 moles of O2 gas. So we can get total moles here. N total equals to 6.05 plus 0.135 moles. And the total moles of gas would be 6.185 moles. Although technically you only keep 2 decimal places. I still write everything out for now, okay? So that's the total moles. If you got the total moles, we can actually go ahead and get the pressure total because you can just get P total and then V total is N total, R and T, okay? So we kind of have all of it. So we got N is 6.185, R is 0.08206, and then temperature was 298. And then P total is what we're looking for. V total was 12.5 liters, because that's a tank right there. And then we can get P total. which is all of this divided by 12.5, okay? And the P total answer is 12.1 ATM. Okay, so that's one answer right there. Now that I got the P total of 12.1, I can get a mole fraction from these guys here. Let's do a mole fraction of helium. So mole fraction of helium, and then after we do mole fraction, we can get pressure, is 6.05 moles, right? Over the total, 6.185 moles. So that's going to give me 0.978, okay? And if I wanted to do the mole fraction of oxygen, I can do two ways. 0.135 over 6.185, right? So how much is that? 0.135 over 6.185. You get 0.21827. Okay, so that's one way to do it. 0.135 over 6.185. And then you end up getting 0.0218. Okay, do that way. Or if you didn't want to do this, you can just say it's also the same as 1 minus 0.978, and that's 0.22. Either way works. They're both pretty much the same answer. Okay? Now that you know this mole fraction here, I can go ahead and get the P of helium, which would be mole fraction of helium times P total, which is 0.978 times 12.1 ATM. Okay, that's going to give me 11.8 ATM. Now, if I want to find a P of oxygen, I can do mole fraction of oxygen times P total and then do that. Or I can just say, well, I know the total was 12.1, and then I'll just subtract out whatever helium was. I can do that a lot easier. So this one's 0.3. Okay, so we got answers. We got total pressure, partial pressure for each one, and the mole fraction for each one. And that is how you do, this one's a super long one, but you know, we basically apply this many ways around. That's how we talk about partial pressure. Now there's another cool partial pressure application. So I gotta show you a picture of that. We're almost at the end, I promise. Right here. Collecting a gas over water. Okay, so collecting gas over water is a lot of ways. A lot of times when we're trying to catch gas in that, we run it like this and trap it past water. Now, if you collect the gas over water like that, you can actually do this experiment. You throw zinc in hydrochloric acid, it will generate hydrogen gas coming out. You can direct your gas through a tube up in the beaker, and this gas here will displace the water over time. So you see it, first the water is like high up and the water is going to keep falling down until you fill this whole thing up. Or whenever you stop the experiment, then you can measure the volume. But anyway, inside this area here, there is two things. There is pressure of the gas of hydrogen and pressure of the water vapor. And that pressure of water vapor depends on what temperature you're doing your experiment in, because on different temperatures, you have different amounts of water vapor pressure. Okay, vapor pressure of water. So if we were doing a room temperature, 25 degrees Celsius, you say, well, my pressure of water is 23.78 millimeters mercury. So that means this gas here
inside here, there's hydrogen gas, and there's also 23.78 millimeters mercury of water vapor pressure. So there's going to be 2 in here. So this one, P total equals to P gas plus P water. And then the P water, you'll look up from the list up here. So I want to show you an example of how we would do this problem here with one last math problem, collecting gas or water. And then we'll talk a little bit about theories, and then we'll be done with this chapter, okay? So let's see, what do I want to do? Okay, let's write this question out. The oxygen gas emitted by an aquatic plant was collected over water at 293 Kelvin and a total pressure of 755.2. Right. So 55.2 millimeters mercury over a period of time 1.02 liters of gas was collected. How many grams of O2 gas were formed? Okay, and then tell you if it was at 293, the pressure of water at 293 Kelvin. This one you'll have to look up from the chart, but they're giving it to you here. 17.55 millimeters. When you're doing your homework, make sure you pull out your e-text and pull out this chart here from your textbook pages. You can look it up either your appendix or just the chapter slide that we have. Okay? Or I guess you can Google it too. All right, so let's put that together. So we want to make sure we want to get grams of oxygen. So we need to use ideal gas law to get moles of oxygen. To get to moles of oxygen, you first need to get the pressure of oxygen. Okay, so P total equals to PO2 plus P water. They gave us a total, right? The total was 755.2 millimeters mercury. And then oxygen is what we're looking for, and then water was given as 17.55 millimeters mercury. So I can get P of O2 here. Wrong unit though. Only convert it, it's fine. 737.65 millimeters mercury. Okay, because you take 755.2 minus 17.55, you get that number. Once you get 737.65, we go ahead and convert it to ATM. 1 ATM is how many millimeters mercury? 760. Okay, so therefore P of oxygen is now 0.97059 ATM. Okay, so we get that ATM. Now we use ideal gas law, PV equals to nRT, all of oxygen. So oxygen's pressure is 0.97059. Volume of oxygen was given, right? 1.02 liters. N is what we're looking for, N of oxygen, so N of O2. Write it out, R 0.08206 liter ATM per moles Kelvin. And then the temperature was given as 293. I will try to write 8, sorry. 293 Kelvin.
And then you get number of moles of oxygen gas would be 0.97059 times 1.02 divided by 0.08206 divided by 293, okay? And you will get your answer for number of moles here as 4.12 times 10 to the minus 2 moles of oxygen gas. Once you get the moles of oxygen gas, we can easily convert it to grams because 1 mole of oxygen gas is how many grams? Remember, it's O2, not O. So 1 mole of O2 is 32 grams. A lot of people put 16 and then you make a mistake there. So make sure you don't do 16. It's 1.32 grams of oxygen gas. Okay, so that's how you would solve this problem right here. Now, we are going to go to the last part, which is a little bit of theory. I'm not going to do any more math now. I want to talk theory now. Okay, that means you got to understand what we're talking about. So not too much. We only have like a few pages left. We want to talk about kinetic molecular theory. So the assumption for kinetic molecular theory, for it to stay true, is number one, for it to be an ideal gas law situation here, we always assume there is a lot of empty space between the gas particles. That means the space that the gas takes up is so small compared to the distance between one gas molecule atom to another gas particle, which is atoms or molecules, depending on what the gas is. Okay, there's a lot of empty space between them. Like one gas is here, beep, the other gas is all the way in the end there. They're not like all stuck together, close together. Gases are far apart. Okay, and then the next thing is that we mentioned this earlier, the average kinetic energy of the gas is directly proportional to the Kelvin temperature. Not any other temperature, but Kelvin, okay? It's very important we stick to Kelvin here. So the higher the Kelvin temperature, the higher the kinetic energy will be. It's directly proportional, okay? Now it's really cool though, as you raise the temperature, the average kinetic speed increases, but don't think that all of them are moving at the same speed because it's just the average. In your sample, I'll show you a picture right here. It's like, you know, they say the average, but you see how there's a spread here? Some move fast, some move slow, but then they average it out. There will be a number right there for that sample. Anyway, and the next assumption they have is basically the collision from one gas to another gas is elastic. That means there's no reaction, there's no energy loss. You're just kind of like bouncing like pool. When you're playing pool, all the balls are just bouncing off instead of like a car crash. When the cars hit each other, they don't just bounce off and nothing happens. That one's inelastic, okay? When you hit the pool balls, they just bounce off each other, nothing happens. This is the kind of interaction they are talking about in gases. Now, kinetic energy is dependent on temperature, remember? And kinetic energy equals to half mv squared. So m is how heavy it is, v is how fast it's going, the velocity. So if you have different kinds of gases, okay, but all of them at the same temperature, that means all of them will have the same average kinetic energy, but they won't be moving the same speed. So the question will be, if I have all the gases, like 3 gases at 25 degrees Celsius, that's the same temperature, they all will have the same average kinetic energy. Okay, and then because they have the same average kinetic energy, the lightest gas, the lowest molar mass, will move the fastest, and the heaviest gas will move the slowest. So sometimes you see a question on a test, they'll ask you, maybe it's at STP, you have 3 samples of gas, O2, helium, and argon at STP. They say, what's the gas with the highest kinetic energy? You'll say, trick question, all of them have the same kinetic energy because they're all at the same temperature. Okay, average anyway, average kinetic energy. And in the same question, they say, we got helium, argon, and oxygen. Okay, now they're saying they're at STP. Which of these gas will have the highest velocity? The fastest one. The fastest gas will be the lightest gas, which will be helium in that case. Okay, so because you know the heavier it is, the slower it will go, because it's stuck on this equation here, and the kinetic energy for everybody is the same. So you can see here the picture. You see how Here's the velocity spread. And it's not like, because it's like average, a lot of sample gases. But the lightest gas, hydrogen gas here, is so much faster. So you see like they can hit up to almost 3,500. And then the fastest in oxygen goes up to like maybe like 1,200. So, but then usually we just look at the middle distribution right there. So this is just a spread of different speeds for so many different, like most of them are going at the speed, very few of them going at the speed. See, majority of them, the amount of molecules are moving at the speed. So you can see that the lighter the gas is, the faster it's moving, okay? So that's that. And then because we knew that the temperature in Kelvin affects the kinetic energy, the higher the temperature, see this 273, and then you go to 2000, your velocity picks up because the kinetic energy is higher now. Okay, the average speed particle increases. All right, the next part we want to talk about is mean free path. When you have molecules of gases in the container like that, it will always be running around. Now, how long it takes to run around before it hits somebody is called the mean free path. Okay, the average distance a molecule travels between collisions, so before it hits somebody, or in between hitting things. It's called the mean free path. The more crowded it is, the shorter the mean free path will be. Agree? So that means the volume has to be smaller, so the pressure will be increasing if your mean free path is going down. All right, so that's the mean free path relationship to how much volume there is. So that's slide number 52 right there. Now, we want to go to diffusion and effusion. Diffusion is the process where gases are going to go from high concentration to low concentration, okay? And then effusion is where gas is going from high concentration to low concentration through a pinhole. So heavier molecules will go slower, a few slower than lighter ones, because it's inversely proportional to the square root of molar mass. Okay, so again, they'll give you a list of gases. They'll say which one of these gas will effuse the fastest, which one of this will effuse the slowest. Well, just pick the lightest one to go the fastest. The heaviest gas will go the slowest. Has to do with effusion rates, and it's actually rate is 1 over square root of the molar mass. Okay, well, proportional to it anyway. And then now we want to talk about real gases versus ideal gas. So this whole entire chapter, we're saying the gases are ideal, but sometimes the gases are not ideal. Okay, real gases do not often behave like ideal gases. When the pressure is too high, when the temperature is too low. At STP, we are at a happy medium. Around 1 atm, around 273 Kelvin, we're good. Everybody's happy, okay? But if you change the parameters here, if you up the pressure too much, or you drop the temperature too much, then it becomes a problem. The gases are no longer ideal. Why? Because ideal gas laws assume that there are no attractions between gas molecules, which this breaks down when the temperature gets too cold. When the temperature gets too cold, the attractions start to be significant. Gas molecules do not take up much space. Remember, we say the gas molecules are far apart compared to the space they take up. Well, if you're squishing them at really high pressure, that's a really, really small volume. The space is getting smaller. They are going to start taking up more significant space. That's when it breaks down. Okay, so remember, high pressure, too tight of a space, smaller volume, it becomes not ideal because it takes up, the volume becomes too small, the gas molecules start to take up space, which breaks the ideal gas law assumption. Lower temperature will create a significant attraction between gas molecules, so that will break that too. So whenever the pressure is too high, the temperature is too low, that is no good for being ideal, okay?
Another thing that can really affect something being ideal or not is the van der Waals constant. It has to do with attraction between gas molecules from one to another. It's intermolecular forces, okay? So in this case here, if you look at this chart here, helium is a noble gas, neon is a noble gas. You see how they're so small? Because they're noble gases, they don't like to react. And then there's some of these other ones like CCl4 gas. It's like 20.4. That one really loves to interact with each other. Okay, so the bigger this van der Waals constant is, the more interaction they have from one gas to another gas, the less ideal it will be. So who is the most ideal gas? Probably in this list, based on that attraction, helium will be the most ideal. Okay, and that is the end of our chapter for gases. And this is chapter 6. So I will see you guys for chapter 7. Good job, you made it.